Great. I believe we can start. So, good morning, good afternoon, good evening to everyone. Thank you very much for joining us today. My name is Mariia Tokova. I'm responsible for the business development activities in the Americas at Chemspace. Today, I will be a moderator. We also have two speakers from the ASKCOS team, Connor and Jihye. I will be happy to introduce them a little bit later. So, before we start, I would like to remind you the webinar rules. So, the cameras and microphones will not be available for participants. Please use the Q&A section to address your questions. We will check it after the presentations. Also, we will select questions and we'll address them to the speakers. Also, the recording will be available on our YouTube channel. So today we will be talking about integration of Chemspace into the ASKCOS platform. So we will show how it works and how it can help facilitate synthesis planning. So we have also agenda. We'll start with the Chemspace platform and then move on the ASKCOS platform. So a few words about Chemspace. We were founded in 2015. We have about 60 people at multiple locations, including Europe and US. We have created our platform for discovering, design, and delivering small molecules. Now it consists of two components, Chemspace Marketplace and Chemspace Discovery, online platform and offline platform, respectively. Our main business is Chemspace Marketplace. So where you can search for and buy in trillions of molecules. I am very happy to announce that we recently added possibilities to search in trillions of molecules, and Xreal is available through our platform. So welcome to try. The platform is supported by powerful search engine. So you can draw your query and search using substructure, similarity, or exact match. Also, if you are looking for query, single query, or list of molecules, and you have synonyms, IDs, CAS, miles, etc., so please try text search and import file. Having this business, we have seen that sometimes our customers need not only compounds, but also help with exploring some collections, libraries. And we decided to establish our offline platform, Chemspace Discovery. And now it consists of a few departments, virtual screening, chemoinformatics team, AI ML platform. We also outsource chemistry and biology services from our trusted supplier, Inamin. Here you can see numbers. Yeah, so about our online platform and offline platform. So we have about more than 20 integrated platforms, over 100 projects successfully delivered, and 60 publications. I would like to focus on our online platform, and here you can see some features which are available through the platform. So again, different catalog options, in stock screening compounds, building blocks, make on demand screening compounds, building blocks, different search options are available. Also ordering process, cabinet and tracking, you can use them. And we also offer compound management activities of one of our offices in New Jersey or Riga, Latvia. Our platform is available through multiple options. So there are public website, custom platform, punch-out site, or Chemspace API. So this table shows what is the difference between them, and you can choose what you prefer. And here I would like to emphasize that Chemspace has been always about collaborations. And today we want to show you one of them, the integration with the ASKCOS platform. And it's my honor to introduce you our speakers, Coley from Massachusetts Institute of Technology. So Connor received his bachelor's degree in chemical engineering from Caltech and his PhD from MIT, followed by postdoctoral training at the Broad Institute. His research group works at the interface of AI and chemistry to develop models that understand how molecules behave, interact, and react, with a focus on therapeutic discovery and the engineering of new molecules. And Jihye from also Massachusetts Institute of Technology. Jihye received her bachelor's degree in chemical and biological engineering from Seoul National University and is now a fourth-year PhD student in chemical engineering at MIT in the Coley research group. Her research focuses on AI-driven retrosynthetic analysis of complex molecules, and she is developer and maintainer of ASKCOS and collaborates actively with pharmaceutical and biotech partners. So that's all from my side, and I'm very happy to will handle the floor to the Connor and then to Jihye. Connor, the stage is yours.
And
Yes.
thank you so much, Maria, for the introduction, for letting us sort of share some updates and information about this collaboration. Um, I think we can switch screen sharing over perhaps to some of the slides from Jihye, if that's okay. Um, so yeah, we're gonna describe an overview of the ASKOS platform. My main role in this will be to provide a little bit of history behind it, then mostly leave it to Jihye to walk through the capabilities, the features, and some demonstrations with this new integration. Um, so I'll start off, go ahead by a quick outline. So we'll be emphasizing an overview of ASKOS, talking through its sort of features, capabilities, its intentions, and then there'll be some demonstrations of that as well. Um, but maybe jumping then straight into thinking about the history behind ASKOS. So ASKOS is sort of an acronym that we use. Most people don't actually know what it stands for, even the folks in the group who work on it. So it started as part of the DARPA Make It project. This was a larger initiative to try to combine AI-assisted synthesis planning with flow chemistry and continuous synthesis. And so ASKOS actually has meaning in automated synthesis for knowledge-based continuous organic synthesis. And the DARPA Make It program, as they phrased it, is really all about automating the way we think about small molecule discovery and synthesis, to think a little bit beyond the sort of manually planned synthetic pathways and batch synthesis. And if you sort of take yourself back, this program was, of course, initiated then and pitched 2013, 2014, and some of these ideas around AI-driven chemistry were certainly not quite as mainstream as they are today. And when we started working on this project, and this is back when I was a PhD student, working with Klaus Jensen and Bill Green, there weren't really any open source synthesis planning tools, despite this being a field that's been around since the 1960s in various form. And there were, of course, commercial tools, but not really data-driven tools either. So that's what really launched us down this path. Now, like I said, on the next slide here, ASKOS and the Make It program was originally about much more than just the AI planning. And so the result of this DARPA program really culminated in demonstrations of how you can combine AI accelerated planning with robotic execution. In this case, it's a flow chemistry platform where a robotic arm sort of assembles the flow path to carry out the synthesis. So you can sort of see the sort of convergence of computational and experimental effort. And this is really what drove this DARPA program. Now, while we were working on this, though, right, we had spent a lot of time thinking about data-driven approaches for synthesis planning, how we can use models to construct sort of recommendations of synthetic pathways. And so that led us to think more broadly about that opportunity, right? Decouple it, let's say, from flow chemistry and robotic execution. And it led us to engage a number of different collaborators and colleagues and partners from the pharmaceutical and chemical industries to think about this bigger role for data-driven synthesis planning to play. So ASKOS became a part of the founding of the MLPDS consortium. That's sort of an MIT industry relationship that continues to this day. And I'm showing here some logos of members we've had over the years, some current and some past. And MLPDS, even if you're not so familiar with them by name, you might know tools like Chemprop, tools like Bolts have sort of emerged in part from MLPDS funded research. So this has been a very valuable partnership that we've had that's really helped us continue these ideas of data-driven synthesis planning. And so that's a bit about sort of the background of how we got here, right? Originally inspired by this convergence of data-driven synthesis planning with robotic execution. But again, we've broadened that to try to develop new computational tools that just sort of equip the pre-competitive landscape in small molecule drug discovery. And so this is where I'll turn things over then to Jihye to take us through the rest of the presentation.
Thank you, Connor. Connor has kindly introduced all of the history of ASKOS, and so I'll move on to talking about the capabilities and features that are available through ASKOS. So ASKOS is an open source software suite for synthesis planning that has a public web page like this. So it's free to use access through the public web interface at askcos.mit.edu. We also have a documentation page that I'll share in the later slides that provide detailed information about how to get started and also how to set specific settings for more advanced usage. We also have the code available through GitLab that anyone can access. So it's currently has been used by more than 35,000 users and also by more than 15 companies worldwide. And one of the benefits that I would like to highlight when introducing ASKOS is that because all of the code is open sourced in GitLab, you can deploy your custom deployment of ASKOS and customize it with internal data sets. For example, these could involve different reactions that you can train models on, or adding your own building block molecules. And so ASKOS is a tool that aims to aid various aspects of synthesis planning. So I hope you can see my laser pointer. But so given a target molecule, ASKOS helps generate ideas or retrosynthetic pathways that can be used to synthesize the target molecule of interest. And once you have these pathways, it also helps evaluate these pathways in silico so that it can help implement these ideas in the lab. And there's various modules available on ASKOS. And to give a little bit more detailed overview of the modules that are available, we see here that ASKOS has various modules for synthesis planning, centered around retrosynthesis specifically, but also with modules that aim to help recommend reaction conditions or predict the outcome in the forward direction. We also have additional utilities, and I will go into more detail about each of these modules in the later slides. So the goal of computer-aided retrosynthesis essentially is, given a target molecule, we would like to propose synthesis pathways that can be used to synthesize this specific target molecule using some combination of commercially available building blocks. And the way that ASKOS does this is that it uses data-driven models, or one-step retrosynthesis models that take in the target molecule and propose sets of precursors that can be used to synthesize this target molecule in a one-pot or a one-step reaction. And so these models, or data-driven models specifically, essentially learn the rules of chemistry from these large-scale reaction data sets. And once we have these models, we can think about applying these models iteratively until we reach a combination of commercially available building blocks. And these data-driven models can be generally classified into template-based and template-free methods. And there's some technical detail here, so it's not super necessary to understand every single detail, but these are relevant for the features that I'll share later. So I'll give a high-level overview. So for template-based models, these are a class of models that use templates, which are reaction rules that encode how substructures in the product side are transformed in the substructures on the reactant side. And so these reaction rules can either be encoded by expert chemists or extracted from large-scale reaction datasets using tools like RDChiral, and that's what we do in ASKCOS. And once you have these lists of reaction rules, the task then becomes predicting the most likely templates that will apply to a specific target molecule of interest. And so these models learn what templates apply for product molecules and then learn to apply it to new molecules that it hasn't seen before. And so one of the benefits of using these templates is that these templates can be linked back to reaction references. So you can look up how these reactions have been carried out, for example, looking at the specific conditions or operating procedures that these reactions were run under. However, one of the limitations of these template-based models is that they rely on these templates to make the predictions. So they can't propose any chemistry that's beyond the scope of the templates that are specified. And so we then have a class of models that don't rely on these templates. So there's several classes within these template-free models. One class of models rely on making graph edits. So you can think about representing molecules as graphs, where you have these atoms become nodes and the bonds become edges. And then the task of retrosynthesis then becomes converting the graph of the product molecule into the graph of reactant molecules. We also have sequence-based methods that essentially represent molecules in a string notation, shown here like this. And then the task is thinking about translating this language of the product to the language of the reactants. So we offer both template-based and template-free models in ASKCOS, and this is a screenshot showing how to use that, and I'll share more about this in the live demonstration portion. So for the template-based model, we have the template relevance method, which essentially operates as I've described in the previous slide. And we also have template-free models. The augmented transformer essentially does the sequence-to-sequence translation. We also have graph-to-smiles, which converts the graph encoding of a molecule to a smiles representation. We also have additional one-step strategies that are not machine learning models. So template enumeration essentially enumerates all the templates that exist in a given template set and exhaustively applies them to the target molecule to come up with the reactants. And the retrosim is a similarity-based method where it looks up similar products in the dataset and applies the templates that are extracted from these reactions that the similar products are involved in. And we also have exact match, which essentially looks up the exact literature precedents in and proposes the reactions. For the data-driven methods, we have a lot of different data sets these models are trained on. And so here you can see Reaxys. And Reaxys is a data set that has reactions that are involved in journal and patent literature. We also have other data sets like USPTO, which are reactions that are published within US patents, as well as Pistachio, which are US and European patent literature, and also BKMS, which is specific to enzymatic reactions. So we have models that are trained on these data sets, and you can select which ones to use here in the strategy settings. If you have a custom deployment, you can also think about training your own model with internal datasets and adding it to your deployment of ASKCOS. And we have in the documentation detailed instructions on how to do that as well. So in the interactive path planning page, this is an interactive way of performing retrosynthetic analysis where you can click on specific molecules to apply the one-step model. And so here we show an example where I've clicked on this specific molecule to apply the model. And you can also click on additional molecules to continue growing the tree to find retrosynthetic pathways. Multi-step retrosynthesis essentially does this automatically. So we have algorithms that does the selection process, then automatically expands the node, excuse me, and then updates the values of the nodes that are in the pathway to iteratively continue going through this process until you find a full synthesis pathway. And so we have the tree builder in ASKCOS that does this automated synthesis planning. And once you run the tree builder search, the results will show up in this My Results page, where you can view the results of the trees that are generated using either the View Tree button or View in IPP button. If you click on View in IPP, then this will populate the interactive path planning canvas with the pathways that are generated. You can also see the various settings that are used when generating these trees. And so the different types of settings you can select are either the tree builder versions or the specific algorithm that is used. You can also select one-step strategies. You can also mix multiple of them as well. And you can select what you would consider a specific starting material, what you want the terminal nodes to look like. And this can be either selecting the building block, and I'd like to highlight CS here, which is the Chemspace building blocks. And you can also select different list of rules of what you would consider a starting material. And this could involve setting an upper limit on the cost of precursors. You can also set different search parameters, for example, the time that you allow it to run. And there's many more settings, and I won't go into the detail about every single setting, but you can see more about these details in the documentation page. And so another thing that I would like to highlight is that adding the Chemspace building block catalog enables us to find routes for more target molecules. And so I'd like to highlight one example of etrasimod, which is an FDA-approved drug for ulcerative colitis. And so when we didn't have the Chemspace building block, the tree search was not able to find any pathways for this specific target molecule. But once we've added the Chemspace catalog building blocks, then it was able to find multiple pathways, and the shortest of which is shown here, where we have this specific molecule that is only in the Chemspace catalog. And so this highlights the importance of having the Chemspace catalog within ASKCOS. And so I've sort of mentioned this, but once the tree builder finds pathways, you might be able to find multiple pathways. The tree builder sometimes returns hundreds of pathways, and so the tree explorer offers a way for navigating through these pathways and ranking them as needed. And so the metrics that we offer for analysis and sorting of these pathways are shown here, where you can sort the pathways based on the number of reactions that are involved in a pathway, precursor cost, and additional metrics like the number of synthetic analogs. And so here is where you would be able to perform additional analysis for each of the pathways. And then you can sort the trees based on different metrics. You can also filter trees based on specific starting materials or intermediates, where you would be able to see pathways that involve either that specific starting material or intermediate that is specified. So this is all for the retrosynthesis portion, and I'd like to move on to the 4 prediction utilities. One module that I'd like to highlight is the reaction condition recommendation module, where given a single reaction, the module proposes or recommends different conditions to run these reactions under. We have the version 1 module that predicts the temperature, catalysts, solvents, and reagents, but we've more recently added Quark, which is a quantitative version where it predicts the amounts of the agents in addition to their identities. And so this is what the condition recommendation page looks like, where here you can see the amounts that are assigned to each of the reactants as well. We also have additional 4 prediction modules. For example, the reaction outcome prediction predicts the major products. You can also think about assessing the plausibility of each of these reactions. And we also have modules for predicting the impurities based on different modes of impurities. And we have modules for predicting the selectivity here, retroselectivity. And now with that, I'd like to move on to the other utilities that we have. And the one that I would like to highlight is this viable search here. We have multiple sources of the building blocks, and I'd like to highlight Chemspace shown here, where you can search for variables in these sources, either using SMILES, the exact search, or you can look up similar building blocks as well using a similarity search. And you can also look for substructure-based searches using SMARTS patterns. And so Chemspace is here as CS, and these pages also offer a link to the building block database. So here, if you click link, by now, this will bring you to the Chemspace website where you would be able to look at different suppliers, lead time, and additional price information. We also offer additional utilities like solubility prediction or solvent screening, where we have models that predict the solubility of neutral organic molecules in different solvents. And I won't go into the details about each of these models, but essentially we have different models that are different in the ways that they operate. Another utility that we have is the QM descriptor, where we have models that are trained to predict QM descriptors computed using DFT, like molecular level descriptors and atom and bond level descriptors. We also have a molecular complexity page where you can compute or predict different complexity metrics, like the structural complexity and synthetic complexity. And we'll show you the computed or predicted values as a table like this. And so that was a very high-level overview of the capabilities and the features that we have on ASKCOS. So I'd like to direct everyone to this ASKCOS Talks, where it has more detailed documentation on how to get started, what each of the modules are, and more. And I'd also like to highlight that ASKCOS is a tool that aims to assist chemists. Because these are data-driven models, they're inherently influenced by the data. And so we always recommend further evaluation using different tools like SciFinder or Reaxys. This slide is specifically for people who are interested in integrating ASKCOS into a more automated platform or a pipeline. And so ASKCOS offers API access with auto-generated documentation using Fast API. There's a lot of people who have made ASKCOS become what it is today. And so I'd like to acknowledge everyone here in the Hall of Fame and the current ASKCOS team who are working on actively developing and maintaining ASKCOS. And we'd also like to thank all of our sponsors and data providers. And with that, I'll see if there are a couple of questions before I move on to the live demonstration portion.
Yeah. Jihye, Connor, thank you very much for the great presentation. Yeah, I think we can go to the Q&A box. Yeah, and indeed, we have a couple of questions. So I believe I can read. Yeah, and then we will address them. So the first one, who are the main users of the platform? Jihye.
Okay, so who are the main users of the platform? I believe there's a lot of different users. I've seen, maybe Connor might have more detailed information about that, but I've seen a lot of pharmaceutical companies. I've seen students or PhD students who are also carrying out syntheses, use them and reach out, and biotech companies as well.
I think one of the things that I'll just add is that I think because it is an open source, sort of open access offering, we do see people using it who might not otherwise have access to some commercial systems or other synthesis planning resources. I think also the fact that it's open source makes it nice and amenable to integration with computational chemistry pipelines and sort of higher throughput virtual screening. So people also might use it to take some generative molecular design pipeline and then filter those designs on the basis of perceived synthesizability. So it's really all over the place in terms of the backgrounds and expertise and use cases.
Yep, great. Thank you. So let's move forward. Hello, everyone. Thank you for the great presentation. When we need not only a synthetic route, but also the executor, can Chemspace help us? Of course. Yeah, we'll be happy to help you with synthesize the molecules, final molecules, as well as source building blocks. So you can contact your account manager or me, yeah, and we will help with this. It's one of our sources. In the ASKCOS platform, how deep in the synthetic road can I go? In other words, can I ask the platform to stop at the step where there are already available commercial reagents?
Yep. That's a great question, and I can answer this one. So the depth of the synthesis route, or depth of the search that you is a parameter that you can set in the strategy settings, and I'll show you how to set that setting on the ASKOS website. Currently, the default setting that we have on the public website is 5, but you can always increase that to identify longer synthesis pathways. And the second part of the question is, can I ask the platform to stop at the step where there are already available commercial reagents? And so it currently stops when it finds what it considers a building block that is set by the specific parameters that we give it. So for example, you can specify it to stop only at Chemspace building blocks. You can also specify it to stop at Chemspace plus a mixture of other sources or any of the building blocks that we have in ASKOS. You can also set a different setting for these, what you would consider a building block. So for example, you don't have to specify any of the sources. You can also just say, oh, I want building blocks that have max 5 carbon atoms. And so these are different parameters that you can set. And I'll share a little bit more about this in the live demonstration portion. I'll take one more question before moving on to the live demo, and then we can come back to all of the questions later. Yeah. So, yeah, Mariia. Go ahead, Mariia.
Yeah, sure. How do you handle unbalanced reaction data in training? I mean, where there is a different number of atoms on both sides, some reactants or products missing, quite common in US patent data.
Yeah, that's a great question. And inherently, the task of retrosynthesis sometimes has to be imbalanced because we essentially take in one product molecule, and this is converted to reactants that can have different leaving groups. And so these are expected, and we don't do any special handling of those. But there's the reverse case where we have a lot of missing atoms in the product side. And this could be due to missing reagents or missing reactants, reagents or reactants being incorrectly classified as reagents, which don't end up in the prediction. And so we do have special filtering stages that are implemented to filter out reactions that have a lot of product atoms that don't really have sources for cases like the temporal relevance model. But some models don't explicitly need or a mapping of the atoms between the products and reactants. And so sometimes it is okay to, it's not prohibited by formulation to have unbalanced atoms in the products and reactants.
Great, thank you. And we have one more question.
Oh, okay, yeah, we can answer that before moving on to
Yes,
the live
I
demo.
think
Okay.
it will be better. Okay, if you evaluate a specific reaction, say from literature, how do you make sure that you get the substrate scope correct for the whole rule?
Yes. So I think this is asking how do you know for sure whether a reaction rule actually applies for the product? So if that is the case, these machine learning models in the template relevance case, for example, is learning to identify when the rules apply for product molecules. So these are essentially learning to differentiate whether the template would apply to a molecule or not. That said, there can be cases where it does look a little bit weird. And so we do have the 4 prediction utilities that aim to help evaluate that in the forward direction. So you can think about using the product prediction modules to give it the reactants and actually predict whether the anticipated product is predicted within the forward predictions.
Just maybe one quick thing to add on there. I think this is sort of a general question that we ask a lot in developing synthesis planning tools, which is what's the right balance between sort of conservatism and creativity? Because the more you deviate from known precedents, the sort of riskier suggestions might be. And I think we've, from a design perspective with ASKOS, tried to decouple to a slight extent the notion of ideation, sort of constructing the retrosynthetic ideas, and then still having a robust filtering and evaluation stage where we rely on tools that Jihye mentioned for evaluation, for example.
Yeah, great, thank you. So that's all from the Q&A section. Yeah, Jihye, I think we can move forward.
Yep. So I'll now move on to the live demonstration portion. So this is the homepage of ASKOS that you'll see when you first log into ASKOS. Currently, I have run a couple searches, which is why it shows the history that you have run. But if you haven't run anything and you're starting fresh, you'll see these a page without these information. And so one of the ways that I like to get started when I am on the page is by typing in or drawing the structure of the molecule that I am interested in. For example, you can type in the smiles of a molecule. You can also just draw the molecule yourself using this draw utility, and it will populate the smiles on this page with the smiles of the molecule that you draw. Another feature is that we have this name resolver where you can just type in, for example, a molecule. And if you click in resolve, it will retrieve that smiles from PubChem and then populate this field with the molecule. And once you have typed in, drew, or entered the smiles of the molecule that you're interested in, you'll be able to see a lot of different tasks that you can run with this molecule in mind. These tools or modules are also accessible through the sidebar on the left, where if you scroll down, you'll see the modules, and you'll be able to access the retrosynthesis modules, for synthesis modules, and the additional utilities described in this presentation. There's also additional tools like checking the server status. Sometimes one of the modules might go down, and here is where you would be able to see if your prediction is not running because the server is down. This is the wiki page, which will bring you to the ASKOS documentation page. We also have tools for reporting any bugs that you find, and we'll get an email if you report a bug through this link. There's also additional tools like My Results, where you would be able to see the results of the runs that you've run. And you can also ban specific molecules or reactions and see what you have banned here in my ban list. And so I'll go ahead and move on to the interactive path planner, which is the page where you would be able to run retrosynthetic analysis for target molecules of interest. And so one of the things that I'd like to highlight is this strategy settings here, and this is where you would be able to select different strategies to use, modify different visualization settings, etc. when you are running the retrosynthesis. One of the most important settings that I'd like to highlight is this strategy plan. And this is essentially what model you're using to run the retrosynthesis. Here, the default that we have is the template relevance model with the reaxis dataset. And so here you can also see additional model types that are available, as well as the different data sets that each model is trained on. So here the default is reaxis, but you can also add multiple strategies using this plus button here and change this to pistachio, for example, which is trained on the US and European patent literature. You can also add multiple strategies, and they don't all have to be the same model type. So you can click Augmented Transformer trained on the USPTO full dataset. And so once you have these strategies, you can click Save. And before I do, I'd also like to mention that there are tooltips available that give you details about what each of the strategies or what each of the settings mean. And so here, for example, top n results to add to the graph means that we'll be adding 5 results to the canvas by default. And so once you have specified all of the settings that you are interested in, you can click Save, click on one step, and this will start running the predictions. If you do add multiple strategies, it does take a little bit longer to run. But once the predictions are run, you can see that the canvas has been populated with the predictions. There's a lot of colors and symbols here on canvas, so you can click on this legend, which will show you or tell you what each of the colors and symbols mean. Once you have generated these predictions, you can click on these nodes. I hope the HUD is showing. Okay. And so here on the reaction details page, you can see the reaction that is predicted, as well as the details about the models that are used to generate these predictions. And one thing I'd like to highlight here is that because template relevance is a template-based method that relies on templates, you can click on template details to see the exact template that was used to generate this prediction. So if you click on this T-forms link, this will bring you to the template information page that shows you the exact template, as well as a link to the reference reactions. For example, in this case, this is a pistachio model that's trained on US and European patent literature. So you can click on this reference link to access the patent page. Now going back to the template information page, you'll see here that there is a number on the in brackets. And for pistachio models, this number denotes the paragraph at which this specific reaction was found under. So back to the template or back to the patent page, you can just scroll down and look for the specific patent paragraph number. Now going back to this page, you can also click on molecule nodes, which will show you details about the molecules themselves. So once this molecule node has been expanded, which means the model has been applied to this, you can scroll through these precursors that are proposed to look at all of the model predictions. We've added 5 to Canvas by default, but you can always add new predictions to Canvas by clicking on this plus button, or remove them as needed by clicking on the minus button. There's other things you can do on this page. For example, if you click on a node in circle, an atom in circle, this will filter the predictions based on whether that atom is involved in the reaction. And so here you can see that the clicked specified atom is involved in this reaction. And so that offers one way to navigate through all of the predictions that are generated. You can also sort these predictions by different metrics like the score or synthetic complexity of the molecule. And you can also see, if you click on unexpanded nodes, the precursors don't exist. And so you can click on this expand node button to further expand that node. You can also double click on the node on the canvas to expand or apply the models to it. And so if you click on this node, for example, it's highlighted in green because it is an available building block. And we see here that it shows you the price and the source that gives you this minimum price, which in this case is the Chemspace building block. And so for building blocks, you can go to Search Bibles page, which will populate the smiles. And once you click on that, you will see these building blocks that are from different vendors. And so for Chemspace, if you click on this link, this will bring you to the Chemspace page that shows you all of the information about the supplier, lead time, and more. Like this. Now, going back to this page, other things you can do on Canvas here is you can save these results to my PC or my account. And if you save it to my account, this will be saved in the My Results page that we've seen in the sidebar. On this page, another thing you can run is the tree search. So if you click Build Tree, this will submit the tree builder search job, and this will run in the background. So you'll be able to run other tasks while this job is running. And once the tree builder jobs are run, then you can go to My Results, which will show you that this is the job that has been started running. And so here, these are 2 results that I've run before. where we've run the tree search with the Chemspace building blocks and without. And we see that we found 200 trees for this molecule with the Chemspace building block. And so once this is run, you can click on View Trees, which will bring you to the Tree Explorer page. And so here is where you would be able to navigate through these trees by clicking on these arrows. Right now, the trees are sorted based on the number of reactions and the length of the longest linear pathway or depth, but you can also change how these trees are sorted to prioritize or different strategies. You can also run additional analysis as shown here, and also filter trees by selecting different starting materials. If you are interested in a specific pathway, you can also add this to IPP, which will bring you to this interactive path plan canvas that's populated with this specific pathway. And then there are additional evaluations that you can run with these reactions. So evaluate reaction essentially brings you to the forward prediction page with the reactants and products pre-populated using the specific reaction information that you selected. You can always access this page through the sidebar on the left and then enter the reactants and products that you are interested in as well. And so these are the version 1 predictions where it predicts the solvent reagents and catalyst identities, but you can also select the quantitative version to run the predictions as well. There's also product prediction tasks or impurity prediction or and retroselectivity prediction tasks that you can run on this page. Right now, everything is pre-populated because we clicked on evaluate reactions on the IPP canvas, but you can also have these, you can edit these yourselves or enter in the reactants that you're interested in. Then we can also see the additional utilities page that has the solvent prediction. Let's copy this smiles. And then once you have the solubility prediction page, you can enter the smiles of the molecule that you're interested in, type in the solvent information and the temperature information, select a model to use, and then submit to run the predictions. And then once the predictions are done, this table will be populated with the solubility values. There's also a solvent screening page where you can enter the same smiles, screen the solubility across a set of solvents and temperatures. We have 2 sets that are provided, but you can also add custom sets as necessary. You can also submit and wait till these predictions are run. There's also additional information that will be provided once you click these model input and output details. I won't go into the details of how these models work for now, but you can always explore them if you would like. And so once the jobs are done, you can see that these solvent screening page has been populated. You can also change how you visualize the results and download the results that you want. And then the QM descriptor page also, you can enter the smiles, submit the jobs, and the predictions will run. And so if you scroll down, there's a lot of numbers on this page. So what I like to do is click on the 3D visualization, where it allows you to click on specific atoms to look at the values that are predicted for this atom. You can also click on to see the details about the bond that this atom is involved in. And then the next page brings you to the molecular complexity, where you can enter the smiles, click different metrics of interest, and submit that job for it to run. Then you can also look at viable lookup, which is a page that we've seen before. And I'd also like to highlight that you can enter this smiles, select different sources to run the search. You can also set a similarity threshold where you would look at similar compounds as well. Yep, and that is all for the live demonstration portion. There's a lot of features that I wasn't able to share through this webinar in the interest of time. So I would recommend everyone who's interested to go to ASKCOS docs and ASKCOS paper on to see more details about the modules and the features that are available. Thank you.
Yes, thank you so much, Jihye, for that very nice presentation overview. Yeah. So let's check our Q&A box. We have no more questions here, but if you still have any questions, you can ask directly the ASKCOS team or the Chemspace team. Yeah, please do not hesitate. Do it. Thank you. Thank you again, Connor, Jihye. Yeah, we are very excited to have this collaboration with you. And thank you everyone for joining us today. So with that, I conclude our webinar. Yeah, so thank you. Thank you, everyone.
Thank you very much.
Thank you for
have a good
inviting me.
one. Yeah, bye.